Hello everyone, my name is Fred Rispoli, and in this video we're going to discuss Chebyshev's theorem. Now Chebyshev's theorem, also known as Chebyshev's inequality, is often studied when people study probability, and in this video we'll give a formal statement of the theorem and then provide a restatement in simpler terms, and this will be followed by 3 examples. So in data analysis, people are interested in knowing how much the data is spread out. Typical measures of variation include the range, the variance, and the standard deviation. The standard deviation can be used together with proportions to help understand the spread even more. For example, there's a well-known empirical rule of the normal distribution that tells us exactly 68% of the data is within 1 standard deviation of the mean, 95% is within 2 standard deviations of the mean, and 99.7% is within 3 standard deviations. Now, Chebyshev's theorem provides similar but lower bound proportions for any distribution. So the listener should be well aware that these percentages only apply to a normal distribution. What we're going to learn about applies to any distribution. Okay, so the formal statement of the theorem goes as follows. If a probability distribution has a mean mu and a standard deviation sigma, then the probability of deviation from mu by at least k sigma is at most 1 over k squared. So in mathematical terms, we get an inequality that looks like this, and this tells us that the probability that a deviation is greater than or equal to k sigma is less than or equal to 1 over k squared. It's a little bit easier to understand this when we consider the complement of this, which tells us the probability of a deviation being less than or equal to k sigma is greater than or equal to 1 minus 1 over k squared. Okay, so let's try to simplify this even more by just trying to state this in easier to understand words. So we can say that the proportion of values from a data set that fall within k standard deviations of the mean will be at least 1 minus 1 over k squared, where k must be a number greater than 1, and it's possible that k is not necessarily an integer. Now, for example, when k is 2, the theorem implies that 1 minus 1 over 2 squared, which would be 1 minus 1/4 or 3/4, which is equal to 75% of the data values, are within 2 standard deviations of the mean of the data set. So notice this is a significant difference from a normal standard deviation. With the empirical rule of the normal distribution, we knew that 95% of the data was within 2 standard deviations. But here we're saying we know that at least 75% of the data is within 2 standard deviations. And this is true for any probability distribution. So here's a visualization with a number line. This is telling us that if I have a mean, and if you think of this interval as being the mean plus 2 standard deviations and the mean minus 2 standard deviations, we get at least 75% of the data in this interval. And if we extend this to 3 standard deviations, then we get at least 89% of the data. So now let's look at some examples. Suppose we know that the mean price of houses in a certain neighborhood is $300,000 and the standard deviation is 50,000. Find the price range for which at least 75% of the houses will sell, and then part B, at least 89% of the houses will sell. So Chebyshev's theorem can be used as noted before. When we have 75%, if we set our 1 minus 1 over k squared equals to 75%, we see that k is equal to 2, and we use the formula mu plus or minus 2 sigma to get a range. So 300,000 minus 2 times 50,000 gives 200,000, and then 300,000 plus 2 times 50,000 gives us 400,000. So to summarize, we know that at least 75% of the houses will sell between 200,000 and 400,000 in this neighborhood that we're interested in. Part B is similar, but now we have 89% and we want to find the range. So 89%, what we do is we set 1 minus 1 over k squared equal to 0.89. Solve for k, do a little bit of rounding off here, and we see that k is approximately 3. Now we use the mu plus 3 sigma to find the range, and you can see we work this out. We get 300,000 minus 3 times 50,000 gives us 150,000, and then with the plus we get 450,000. Our summary is now that at least 89% of the houses will sell between 150,000 and 450,000 in this neighborhood of interest. Example 2. Suppose we know that the average cost of a certain type of ticket is $100 with a standard deviation of 15. Use Chebyshev's theorem to find the minimum percentage of data values that will fall in the range of $80 to $120. Notice that this problem is different from the previous example because now we're given a range and we want to find the percentage. In example 1, we were given a percentage and we were asked to find a range. So the solution, first we must find k. The idea is to set mu plus k sigma equal to 120. Substitute in for mu and sigma and then solve for k. This gives 100 plus k times 15 equals 120. We subtract 100 from both sides, divide by 15, and you see that we get k is equal to 20 over 15, or approximately 1.33. Next, we'll use our 1 minus 1 over k squared formula with k equals 1.33. When we work this out, we'll get a probability of 0.4347. Now we could summarize and state that at least 43.47% of the concert tickets will sell between $80 and $120. In our last example, we'll notice that we're given the number of passengers who arrive at the platform in a New York Amtrak train station for the 2 p.m. Saturday train is a random variable with a mean of 180 and a standard deviation of 25. Find the lower bound probability that there will be between 80 and 280 passengers. Again, first we find k. In fact, in all of these we find k. So now we set mu plus k sigma equal to 280. Right? I could use mu minus k sigma, but then I would have to use the lower bound. But either way, we would get the same answer. When I substitute in 180 for mu and 25 for sigma, we'll get an equation that looks like this. Now we solve this for k, subtract 180 from both sides. So that would give us k times 25 is 100. And then solving for k, we get k is 4. Go back to our 1 minus 1 over k squared formula with k is 4. So this would end up giving us 1 minus 1 over 4 squared, or 1 minus 1 over 16. And when we simplify that, we get a probability of 0.9375. Summarizing all of this, we can now say there's a probability of at least 93.75% that the number of passengers that arrive for the 2 p.m. train is between 80 and 280. So I hope this video helps. This is the end. Thank you for watching.